So a lot of times we think of reactions as happening very, very fast, and some are. We think of lighting something on fire. It catches on fire very, very quickly. That's a very, very quick reaction. But not all reactions are that quick. And so it might take a very, very long time for a system to reach equilibrium. So scientists then need a test to tell whether or not a system is at equilibrium. So think of this test like a before and after test, where you know what you started with and you know what you should end with. And if you compare those two numbers, you can figure out, well, is it at equilibrium or is it not? And the thing we use for this is called the reaction quotient, which is symbolized with Q. And this would be our before, and our K would be our after. So when a system is at equilibrium, it has this value right there. Before, it would be at Q. And so the Q value, you guys, is nothing more than a test. It just answers a question for us. And the question that answers is this right here. Okay, it's nothing more than that. So it's going to let us know, did this reach equilibrium? And if not, which direction does it have to move to get there? Does it have to produce more products or more reactants? So as an example right here then, we see that the Kc for this particular reaction is 0.042. So the equilibrium constant is that value at this temperature. And a scientist who is looking at the system finds these concentrations right here at this current time. And to calculate the Q, it looks identical to the K, to calculating the equilibrium constant. The only difference is that you use the initial concentrations of products raised to all their powers divided by the initial concentration of reactants. So in this example then, the Q is going to be equal to the concentration of SO2Cl2 divided by the concentration of SO2 times the concentration of Cl2. So then to figure out what the value of Q is, we would use the initial concentrations, which are given to us. So then we just solve like we would for a K, and we find that Q is 15.6. Now all that we've done here is we've gotten a value that we can then compare to the Kc. So we know that the Q equals 15.6. We know that the Kc should be 0.042. And what we find here is that the Kc is not equal to the Q. So that means the system is not at equilibrium. So let's compare these numbers then. What we can see here is that Q is greater than Kc. So let's remember that both Q and Kc are the concentrations of products over the concentration of reactants. So then what would make this value greater than this value? Well, it would be too many products, because more products is going to make Q bigger than Kc. So in order for this system to reach equilibrium, it has to decrease the products and increase the reactants. What we'd say then is that the system has to proceed or shift to the left. So it has to create more reactants in order to reach that equilibrium. So here's the reaction again, and what we found from the Q is that there was too many products, so the concentration of this was higher than what it should be at equilibrium when it's got that perfect ratio that it's set up. And so the reaction is going to have to shift towards the left, thus turning some of the SO2Cl2 into more Cl2 and SO2 until it reaches equilibrium. And so the SO2Cl2 is going to decrease, the sulfur dioxide and the chlorine gas are going to increase, and then the system will reach equilibrium. And at equilibrium, the ratio would be that 0.042 that it was, or should be. So think of it in terms of numerators and denominators. But if the Q is greater than the KEQ, that means there's more products than what there should be. And so it's going to have to shift towards the left, so to increase the reactants in order to achieve equilibrium. If the Q is less than KEQ, that means there's too many reactants, so the number on the bottom is larger, which means that the reaction is going to have to shift towards the right. It's going to have to produce more products until equilibrium is established. And finally, if Q is equal to KEQ, hey, everything's peachy. It's already at equilibrium. Keep being awesome, system.